Hey y'all, it's Dr. Know-It-All. Today I'm going to talk with James Douma, who is an exceptionally bright, gifted person who's worked in AI for a long time, as well as a whole bunch of other things. You'll see we end up talking about a whole bunch of different topics. It's a blast. I had a really good time talking with him, and we're planning on another chat in the near future. So anyway, the conversation goes all over the place, so be prepared, strap in. There's a lot of technical details in here, so if you really want to geek out, have a lot of fun and talk to us about investing, about Tesla, about consciousness, about AGI, about neural networks, AlexNet, you name it. We talk about a whole bunch of things. So pull up a chair, get a cup of coffee or tea, and join us for a really awesome conversation.
So I'm just like at my core, I'm a super hardcore engineer. Like I always have been. It's like I was one of those kids that like my parents all knew exactly what I was going to do when I was like 3 years old, right? Like I didn't go through school. There was none of this soul searching. Oh, maybe I'll be an artist. Maybe I want to be an astronaut. No, it's like I was going to be an engineer, like all the way back. The funny, and I did fine as an engineer. I was well compensated. I worked in Silicon Valley. It was a comfortable existence, that kind of stuff. But I didn't start making money until I quit my job and started investing.
Interesting.
So it's and I didn't think I would be good at it, and I didn't think. I'm pretty conservative. Engineers are conservative. That's an interesting thing that I learned, and which. I did. So I helped people build high frequency trading systems at one point. So like I knew things about the stock market, and I had a lot of friends who were super into day trading and all that kind of stuff. And I watched them get their clock cleaned, and I learned about what the world was like and all that kind of stuff. And it was never for me. But then, when you're retired, you got your savings, you got to do something with it, and you start paying attention. You start thinking about that kind of stuff. And at some point, if you're an engineer in this day and age, stuff that is really useful for separating the BS from reality, and being able to make decisions. And, it is just, I'm super conservative. I make super long-term bets. I only do stuff where I feel like I have an advantage, where I myself know something based on my experience, right? And it has worked great. And of course, a big part of that is I was lucky to be born into an era where the kind of stuff I'm interested in and the kind of stuff I read for fun and the kind of things I do for fun, they feed into they feed into important decisions that you can make about investments, and they let you, and very few people have that advantage, right? So like if you're an engineer and you're into this stuff, I started with, I had my retirement savings. I took 10% of it just to play with. And that 10% is way bigger than all the rest of my portfolio is now by a large margin. So I get the comfort of like, I've got money that I can live on. No matter what happens, I'm okay. Because I'm just playing with the fun money part of it. But the fun money part is, it's 95% now or something like that. So it's just a big game, right?
Yeah, no, that makes sense. It's kind of, I think it was, is it Stephen Mark Ryan? I mean, a lot of people say this, but he always says that gap between your knowledge and the market knowledge is where you can make an investment and make money, because by the time they catch up, you've already invested so that you've got it. But anyway,
I'm actually a little more conservative than that. There's Peter Thiel has this line. Like I haven't read any of his books. I don't know much about him, but he has.
I love his Zero to One is a great book. Peter. Is it? Yeah, it's Peter Thiel.
Peter Thiel. He has this line, which is like, what it's like. What do you know is true? What do you know is true that the rest of the world thinks is false, right? So when there's small, and that's pretty much what I've done. Like I looked at places where I looked at something based on my background, my conviction, my research, and that kind of stuff. I would see something that the rest of the world was just totally getting wrong. Right? They were just wrong. I knew they were wrong. And like, it did the research, it did the homework. I'm like, how can they be so wrong? Right? And you're like, I might not know if I'm right for 5 or 10 or 20 years, maybe, but I'm right. I'm really convinced I'm right. And so, you go in on that. Right. and it takes time, but in the long run, it pays off. I mean, you're certainly young enough that it's not like you're going to be giving it to your kids, right?
Yeah, exactly. Well, my kids would disagree. They'd probably want it, but actually, one of my my oldest son, who's 27 now, convinced me to actually mine Bitcoin right at the time when it was getting really hard to do it as a personal computer-based thing. So I ended up with a few Bitcoins. So that's pretty cool. That's a nice little thing on the side that's just sitting there. So yeah, so I mean, I'm like you. I'm a super conservative investor. I've never actually sold a single stock. So I've bought over the years, I bought a lot of Apple, and I would actually have a lot of money because I bought Apple in the 90s. And I would be very wealthy right now, except that I got divorced. And somebody else now has all of that stock, which is like, just makes me cry every time I think about it. So anyway.
I have an acquaintance of mine. She got divorced, and the one thing that she wanted in the divorce was the Tesla stock, because she convinced her husband to get it. Like, he wasn't even into it, and she got the Tesla, and all the stuff she really wanted. That was the thing. And it was right around the time that Tesla took off, and then she couldn't get it all. It was super grim.
Yeah. No, it was exactly like that. I basically said, we had no money in the 90s, and I was like, can I take like $1,000 and just do this fun money? I was like, here's some money that we don't need right this minute. Can I do that? And then she got a much better lawyer than I did. And he was like, we are taking all of that. So,
sometimes those guys pay for themselves.
Oh gosh, yeah. I mean, anyway, that's a whole long story. All right, let's circle around, because we're talking about this. I want people who don't know you to get a really short, like, just pertinent to like AI technology, stuff like that. Super short bio on you, and then I'll do one on me, just like 3 or 4 sentences, just so people have a sense of where we're coming from when we're talking about this stuff.
I'm a dilettante. With everything pretty much. But I've been doing AI, and especially machine learning, for a really long time. It's the stuff that's probably relevant to this is around in the early 2000s, I started really fiddling around with it a lot. And I kind of went part-time at my job and joined a research group in 2007. And we were actually working on problems that we were like, why don't neural networks work, and what needs to change about them? This is back in the era when they didn't work. And our, the thing we were thinking was that, the nodes need to be more powerful. You need to have more than just like one bit or one integer passing between them. So we spent a bunch of time looking at that. And so I had my head down on that work around when the ImageNet thing happened. So I didn't hear about ImageNet for, I don't know, like a year or something after it happened. And then I was like, okay, I'm done. I dropped like everything I was working on. I was like, this works. It really works. I'm going to figure out, I'm going to learn everything I can about how this works, because this is big. This is really going to change the world in a big way. And so basically, I quit my job actually after that happened. So I was working at an optical fiber startup, and during the bubble, right? We were actually like the 5th biggest IPO in history. Like I wasn't like a founder or anything like that. I was kind of late into the mix, but so I spent the early 2000s designing, gigabit fiber optic transceivers and all the stuff that went into those. And it was super fun. Like I learned a lot of stuff and whatnot. It wasn't AI related, but I went part-time at one point, like in 2007, when I started working on this, when I was like, I really need to get back to ML, because that's really what I want to do. Like,
Right.
And it was hard to extricate myself from this company that I'd been in. So I was part-time with them for a while. And then ImageNet happened. I'm like, okay, job over. We're going to do this. Right. And so basically since then, I've just been looking. It turned into looking for investment opportunities. Originally, when I quit, I was like, oh, I'm going to start a company doing this stuff, because there's so many opportunities. And so I have collaborators, I guess, partners in crime. And we started a study group to try to figure out like what businesses are well poised to, like, what would you go into to really make this work? And it never turned into a company, but it turned into a lot of great investment ideas.
Right.
So unfortunately, I'm the only guy in the group that was investing all the time this stuff was going on, right? So like I made out like a bandit, and they're all like still looking for the company. So
Right.
I don't know how to feel about that exactly. But anyway, so that led me to Tesla. So I ended up, so I actually worked at an EV startup in the 90s. We were making tech for electric vehicles. And that's a hard business. It's a really hard business. Emily, I can get into the details of that at some point if you're ever interested. But I was, after that experience, I was like, man, I don't know if you can make EVs go. And so I knew about Tesla for, from when they started. And it was really interesting. I'm like, but man, that's an EV company. That's really, really hard to do, right? So I didn't look at it.
By all rights, they should have gone out of business. I mean, it's really difficult.
It's super hard. And it's hard for all the wrong reasons. It's not like the tech doesn't work. It's, the car business is a hard business. And I don't know. Anyway, it's hard for all the wrong reasons. And I was skeptical about whether that could do. But then, I've also been really interested in self-driving cars since way back in the day. I went to the DARPA Grand Challenge. It's not far from here. And so like I was there at the moment, right? I was there the day that it became really clear that self-driving cars were possible. Because prior to the DARPA Grand Challenge, you didn't know. Like it'd been a dream for 100 years. And, so many experiments had been done. But there really hadn't been traction. And at the DARPA Grand Challenge, it seemed like we just went through this phase change. Like it went from everybody's like, oh yeah, it would be great, 50 years from now, right after we get flying cars, we'll have self-driving cars, right? And it went to, oh my God, we're going to have in 5 years, 10 max.
What year was that with the Grand Challenge?
2007.
Yeah, okay, that's what I was trying to remember because I'd seen experiments with it in the 90s when it was really just and the whole car just had, computers everywhere.
You can barely drive, only under certain circumstances. And they're all, sort of proof of concepts for one little part of the problem. Right. But nobody thought it was a real thing. But then at the DARPA Grand Challenge, it really, you stood there on the intersection and you watch these things go by and you could, I mean, they were so humanistic that you could tell the personality they had. This was like a young, aggressive driver, and that one was kind of like a granny or whatnot. I mean, you would totally anthropomorphize them, and they're driving in traffic with humans. I mean, they hired stunt drivers to drive real cars to make traffic and stuff for them. It was great. It was really awesome. So of course, I've been thinking about neural networks and self-driving for a really long time. And I've closely followed Google's, efforts and, the big dogs in the space. I was watching them the whole time that this is going on. And then when, after ImageNet, when deep learning took off, I was like, yes, finally, we're going to break the logjam. Because there was this whole era of self-driving after the DARPA Grand Challenge, but before deep learning. Right. When you have
5-ish years, I think, if I'm remembering correctly. Was it 2011 when ImageNet happened?
Google started in 2009, right?
Yeah.
And the DARPA Grand Challenge, the DARPA Grand Challenge was in 2007. Google got into it in 2009. And then ImageNet happened in 2012. But
2012, right? So it's been 10. It's only 10 years ago. That's the thing that blows my mind. Is how recently AlexNet existed. That's crazy.
Yeah. Well, and like the size of the models has gone up an order of magnitude every year. And like for 1 or 2 years, you're like, what a fluke. But it's done that for like 8 years now, right? It's just nuts. Anyway, I was like, neural networks, people need to be putting these in self-driving cars. You need to just like rethink the whole problem because self-driving, it's a vision-centric task. There are things that you can leave out. You cannot leave out vision, right? It's, the right sensor is the camera. If you do a really good job with the camera, you don't need any other sensors. And you only need other sensors to the extent that you can't do the camera well. And when we couldn't do cameras well, and prior to ImageNet, we could not do cameras well. Right. Supplementing with other sensors, that was a super important thing. But then all of a sudden, in 2013, 2014, it wasn't clear that we were going to get cameras really well. It was still a little sketchy. Like the field was, is this going to scale? What kind of accuracies can you get to? Does the hardware have to, it was such a big change in such a small window of time that it took a few years to die, which is one of the reasons why, like, Elon apparently decided in 2014 that to like go all in on this. And like, I was looking at it really closely at 2014, and I wasn't like, and I'm a super big booster like on this thing, and I wasn't sure you could do it. And he was just apparently, in retrospect, we now know that he was all in, because by 2016 they had a product. Anyway,
right. Originally with Mobileye, I know, but I think to try to help people out a little bit here, I'm going to do like my real super brief background here in a second, but I think people don't understand everything's neural networks these days, and everybody thinks about neural networks, and they think that that was always AI. But what happened was, before that, whether it was PCA or SVM or whatever, it was all these features. People would say like, oh, I'm going to code in, essentially, this is what a curb looks like. And that's a very brittle, fragile thing. And people they would code hundreds of these little things that's what vision was looking around and then going through all of this hard-coded stuff to go like, oh yeah, I think that's a curb. But if you imagine, if you drive past that, the curb is always changing, the light's changing.
And it kind of worked. Like, it worked well enough that people wanted to keep working on it and figure out, like, how do we make it a little bit better?
Right.
But yeah, it wasn't
incredibly fragile. I think that was the big thing. Yeah.
So, well, and that was a criticism of neural nets too for a really long time. That they were, in fact, even after the ImageNet results, Alex and the ImageNet, there was an assumption, because people had been looking at SVMs and whatnot for a while, and they'd seen that, like, when they first started working, they were great, and people built some applications, and then they hit the limit. And everybody in the field was expecting neural networks. It's like, you're going to go up an order of magnitude, and then you're going to hit a limit, maybe two, something like that. And then it just didn't happen. And then OpenAI went and they did a bunch of work, and they're like, hey, you know what? If there's a limit, we're not going to see it for a long time. It is like way out there. Like, we got a long way to run. I've
actually thought about that a lot, because one of the things, and so I'll actually wrap my biography into this, but I'm 57 now, which is crazy. But I happen to be born at a very bad time for AI, because coming through high school, I really, really wanted to get into that. But computer science departments really didn't exist to a large extent yet in the early 80s. And AI had fallen off. I was a huge proponent of AI when I was growing up, but then I realized that everyone was like, oh, AI was overblown. The promise was overdone. It's never going to happen. Don't go into it. Terrible thing to go into.
I'm 56 incidentally.
Oh, so there you go. So we're,
I'll be 57 in like a month or two. So we had exactly the same experience.
Right. Yeah. Actually, born almost. I was just born.
Yeah. So get out of college. You're in the middle of AI winter, and that there was that little flowering of neural networks briefly.
Right. Jeff Hinton and those guys.
It happened.
But it was. Exactly. So so I got into Princeton actually as a electrical engineer, but they didn't have a computer science program, and I wanted to do CS, but I didn't want to take all those other classes, so I switched to physics. So I got a degree in physics and met. It was a very humbling experience. There are some really, really smart people who went to school and did physics there. So anyway, but then I went out and I just jumped ship. I was like, I really wanted to be an astronaut, or I wanted to be like a coder and to work on AI. And both of those things had just completely gone away, because it was the end of the Cold War. Nobody wanted astronauts, so I was like, screw it. I'm going to go and get an English PhD. So I did that and did a whole bunch of computer modeling on language in it, kind of naively. I didn't really know what I was doing, but that's part of my dissertation. And then went on and discovered 3D animation, and that was like my baby. So I've been doing that and teaching that for decades, and sound design and editing and things like that are related to it. And then I actually went back to school at UGA, where I'm teaching I did one class at a time for like 3.5 years, and got a master's degree in AI back in 2018. So it was kind of coming late to the party, but it was the thing that I'd wanted to do my whole life and hadn't had a chance to do it.
Not a bit, think of it this way. Think of all the time you didn't waste working on techniques that didn't work very well, right? That's how I console myself over this. Like, I could have been pounding my head against the wall for years and years, only to see, George Hinton and a couple of grad students show up and say, hey, here's how it works.
Right. Yeah, exactly. Oh, I mean, all those people, like, because they were, I'm trying to remember, AlexNet got up to something like 75% accuracy on the ImageNet challenge.
Yeah.
And I think the state of the art was something like 50% at the time.
Yeah.
It was, so all those people who had spent, a decade, 2 decades working on this, and they're like, I got 51%. And then it's like, oh crap. They just
think about you look at the AlphaFold results, like, because that's how I feel about those guys, right? In AlphaFold, that DeepMind shows up once again, it's a small team of guys, they work on it for 6 months and like, boom, right? And then a year they come back and it's like solved, right? Like that's no, man, I don't like that problem has been around. You remember folding at home? Did you ever get a place?
Yeah. I use that along with SETI at home and folding at home. It's such a big problem. It's such an important problem. It's been around for so long. And, and deep learning made it go from like, oh God, it's nuts, the fact that they solved it so fast. Or like, I love the Go story too. I like that they made a documentary out of it, because like I can sit my dad down and say, this is why your son is a fanatic. Right here. Right. Wait, there's a documentary on how they did Go?
AlphaGo?
Yeah, you'll have to send that to me.
Oh yeah, you can watch it on YouTube. It's great. It's super great.
Wow.
Yeah, I'll give you a link so you can put it in the show notes.
Yeah. In fact, I'll put it in the show notes.
It was on Netflix for a while. It's been on a bunch of things. You can watch it for free on YouTube now, I think.
Right. Okay. Oh, that's amazing. Yeah, I've just always been. It was mind blowing enough when they solved chess in the 90s and started beating the best players, but everyone was like, Go is just, well, actually, this actually relates to other things here. So I think one of the reasons why people were so into AI back in the day, like the 50s and 60s originally, was that it was able to do games which human beings considered to be very difficult. Yeah. That was intellectually challenging for us, whereas walking and talking and seeing the world, people didn't realize we'd had hundreds of millions of years of evolution to get there. So it seemed really easy. But when we started looking at that, the easy problems were actually the incredibly difficult problems, including for Tesla right now, self-driving, because you have to be able to see the world and not just see it as a bag of pixels, but what is that thing? What is that thing? That's a surfboard up there. These are books over here. This is a human being. All of that stuff we take for granted, but that is exceptionally difficult to do.
Yeah, humans are pretty bad judges, actually, of what's easy and hard because of our nature. So I did one, as part of my research, I taught myself Japanese. And gosh. So the point of the exercise was to get really familiar with how hard. I don't want to go down that rabbit hole. Anyway, let me point this out. You and I are both, as we have this conversation, we are engaging in an extraordinarily sophisticated, sort of transference of concepts into like a bit stream that I can, I'm modeling you and you're modeling me, and I'm generating language and you're getting it. And we don't even think about it. Like, I don't even have to think about the language part of this. I'm just think about what I want to say, and the rest of it kind of happens. Now, you learn Chinese, right? And you immediately discover it's really hard. Like, language is so hard. And yet, as human beings, it's like the air we breathe. Like, we live in a world full of language. We hear it, we read it, we speak it all the time. It's completely effortless. And driving is like that. It's, to the computer, it's learning Chinese, but to us, we're speaking English when we get in the car, right? We're unaware of how hard it is until you like have to make a computer do it. And then you discover, oh, wow, it's really, really hard.
I think that's a pretty valid analogy. I've never tried to learn any non-Arabic language or non-Western language. So, things like Spanish and French and German and so, where the alphabet is basically the same thing. But I've always been terrified of like Japanese and Korean and Chinese, where it's like, oh gosh,
I pick Japanese. It's the hardest, right?
Yeah, right. Yeah. Is it kanji? Is that the alphabet? Is that what it's called?
Yeah, it's more. I mean, if you look at there's a there's a U.S. government organ that exists to basically teach foreign languages to diplomats and whatnot. And they have a ton of data because they teach a lot of languages to a lot of different people. They have a lot of data on how long it takes, like an American, to learn like whatever language, right? And you can look at the stats, and like Japanese is the one that takes the longest because it's got the biggest space between English and yeah, Chinese is pretty close, right? Chinese is tough. But Japanese is slightly farther, and there's slightly more material to work from. So like it was hard for the right reasons, like because it was informatically hard, and not hard because like Navajo is hard. But one of the things that makes Navajo really hard is there's no material to learn from. There's, you know, you can't get movies in Navajo and like make yourself listen to them.
Right. That's true. Wow.
Anyway, yeah. So it's a super humbling experience. When I started, there was a blog of a Chinese learners who said that he had heard when he started that learning Chinese would be a 5-year lesson in humility. And 10 years later, he said, I misunderstood that when I heard it, because I thought what it meant was that after 5 years, I'd know Chinese and I'd be humble because it had been so hard. What I didn't understand was that after 5 years, I would know no Chinese. But I would be humble. Yeah, Japanese is like that too.
Given the accident of birth, however, if either of us had been born in Japan or our parents had moved there when we were babies, we would know it like no problem right now.
English is hard. English is super hard. I mean, you can look at you probably know this stuff from being an English major too, but English as a language is not an easy language to learn. It's got a lot of interesting characteristics that make it really tough. And yet here we are, it works, right? And you and I, it's as easy as breathing, right?
Right. Yeah. Oh gosh. I mean, we can go down the whole rabbit hole of deconstruction theory and all that. I mean, because a lot of the stuff that I've studied is about how little we actually communicate with each other. The fact that we're able to communicate anything is almost miraculous. That we're able to model each other's brains and think about like what the other person is doing. And yeah. So anyway, so let's talk self-driving cars.
Yeah.
because I think all of this stuff is related to it, because trying to make sense of the world in the way that we humans do, kind of automatically after a couple of years after we're born, we figure it out. But again, I would say, even though if you look at children, little babies that are born, they have the wetware that's available, but it takes a long time. It's not like we don't give a 1-year-old a car and say, go out and drive. You're 16-ish before you're allowed to. So all of these things are incredibly difficult. We just don't give it any credit. That stuff that the baby's doing that we think they're doing nothing, their brains are going like super active and making connections and language and physics. They drop stuff and they see what it looks like when they drop it over and over and over and over and over again, that kind of stuff that's super annoying. So so I mean, so let's talk cars. I guess let's just start with do you think that Tesla's vision only approach is the right approach? Yeah. Okay.
Absolutely. I do. And I was, I said that before, before deep learning, cameras sucked and you had to have other things to supplement them to try to fill in what you couldn't do with cameras. If you can make cameras good, you really don't need other sensors, right? And here's the deal is that if your cameras are sufficiently good, you don't need it. If your cameras aren't very good, you can try to supplement, but supplementing is really hard. It's really hard, right? Because to the extent that your cameras aren't good, they're not good. Right. And to drive well, you really got to have good cameras, right? So doing the whole HD maps, to localize yourself perfectly. Lidar is mainly used for localization on robotaxis. Now they use it for other things. People tend to think of it as obstacle detection, but localization is like the central thing that it started out doing. And it's the most solid key component of the thing that it does. So if you precisely map an area and you have HD maps, right? Your car now, it's kind of a train, right? Like you've turned all the roads into tracks, right? And so now what you've got is you have
I tend to call it a roller coaster, but the same thing, yeah.
Yeah, sure.
It's just on the tracks and it's driving down
the trolley problem, yeah. So now it's a trolley, it's running on tracks. And so there's a lot of the problem you've taken off the table. Now you still have to do a lot of other things really well, but you've narrowed the scope significantly, right? And that was a big part of why you needed that stuff. If you have really good cameras, like you don't need to do that. You don't need to simplify the problem. You can go at the core problem of driving the way people do. So it's reasonable. When I say reasonable, it's not easy. It's reasonable for Tesla to say, we're going to develop a vision system and it'll be able to drive in Bangladesh or Brazil or, Saskatchewan. Like if a human can drive, it'll be able to do the driving because humans just drive with vision, right? I mean, if there's fog, there are situations where humans can't drive and it won't be able to drive, and that's okay, right? And then the whole see in the dark. Well, cars have headlights. Humans do okay with headlights in cars. We design our roads to make them so that they're usable to the cars that we have with the drivers that we have. And so if we can come up with a machine that has an operational domain, which is a functionally equivalent to a human being, and that's vision, that's cameras, right? Now, all of a sudden that drops into the world that we already have. The cars don't have to be connected. We don't have to put wires in the pavement or magnets. We don't have to change all the lights or the signage or that kind of stuff. And it can go anywhere. It can use any road, right? Not just highways, so it's the right way to do it. But we didn't have the key tool, which was the ability to make vision really good until deep learning. And once we had that, that was the right way to do it.
So let me ask that, because I think you're actually putting two concepts together. Mm-hmm. Are you talking about hardware vision or software vision?
I'm talking about endowing a machine with the ability to see with the same kind of faculty. And part of that is hardware and part of it is software. So it's mostly a software problem. To be honest. Now, it's turning out like a few years ago, I thought that GP106, that GPU that Tesla put in the first version of hardware 2 and later in hardware 2.5, like I thought at the time when I was doing the math, I like, that looks like enough to me. I think you can do that. It's 5 tops into 8 of performance. And when I was looking at like how neural networks were scaling, then like how big a neural network could do how good a job, right? Like I was thinking, it's there. I mean, because you've got two things going on. There's the research networks where you just make them bigger and bigger and try to figure out what this is. Right. But then when you sit down and you really start optimizing things, then you figure out how to get the same performance out of something that's 10 times smaller or 100 times smaller with these new technologies, right? And so I was expecting, the research problem might take 100 tops. But once you've optimized it to run in this embedded system that you're putting out in the car, now it's back down to 5 tops and you can do it, or 10 tops, right? A top is a trillion operations per second. Right. So you're going to hear that word a lot in this conversation. Yeah. But here we are, they have 144 tops now.
Yeah. And do you think the hardware 3 is going to be good enough? Do you think because now it sounds like they're not redundantly using they have 2 of those. And it sounds like Carpathia et al. Are actually using both of those chips now independently, whereas it used to be they were running the same code redundantly. So it sounds like they're pushing things.
They never did run code redundantly. I think that was kind of a misperception that people. So the people I talk to who look at the code and the code that I've looked at, it's never been redundant. That's a really simple way to talk about why having 2 chips gets you redundancy. Elon later made a comment, which I think is a better way of actually thinking about this, that like, on a 2-engine plane, you can have an engine out event and you can still get back. And that's not because the engines are redundant, like the 2 engines together produce the same power. And I think that's the way the code ends up getting structured. You got a ton of modules. They do a bunch of different things. And then if you have a chip down situation, what happens is you run some of the functions, you dial down the frame rate to fit into the compute envelope that you now have that's reliable. And you're in a kind of a limp mode, right? So you won't move as smoothly through traffic. You might lower the max speed that you go. I mean, there are all kinds of ways that you might want to constrain the operational envelope of the car when you have a chip down there. But all you're really trying to do is get to the side of the road so you can rescue, right?
Trying to find someplace safe to stop the car. So yeah.
Potentially that's what you get. I do think, you know, I mean, it's an interesting thing to think about. The more compute you have, and I mean, you know this from neural networks, like, you know, you can just make a neural network bigger and train it with more data and it'll get more accurate, right? I mean, it scales kind of logarithmically. So, you know, for every 2x or 10x bigger your neural network gets, you get kind of incrementally better on the, we think about accuracy as like going from 0 to 100 and trying to get close to 100. You can flip that around and talk about error rates, right? And so, you know, and it seems like, you know, you make the neural network 10x bigger and the error rate goes down by 2, or you have a better technique or more data and the error rate goes down by 2. And the question is, you want to couch the problem of like, what am I asking the neural network to tell me in terms where you can tolerate some amount of error and still get there safely, right? And then the question is, you also want to couch the problem in terms where you can make progress, you know, down that you're not going to hit a wall. And so that's part of the challenge of like figuring out how to map a neural network onto the problem from an architectural standpoint, right? But once you've committed to one of those things, you ride that curve for the most part. Now, Tesla has reformulated their solution a couple of times, you know, since I've been watching them do this stuff. And I think they'll probably keep doing that. It's because they'll work on something for a while and they'll realize, oh, you know what? If we reformulated the problem this way instead of that way, now we got to throw all this stuff out and we got to rebuild all these things. But it's a better way to do it, right?
I give Tesla a lot of credit because I don't think people realize how much like ego, and I'm not saying this in a bad way, but if you've committed years of work to one path, it's really hard to go like, throw it away. Let's do this. You know, it's there's a lot of ego that is involved. You have to just get rid of that and say, yeah, we're going to do this because it's the better solution.
The sunk cost fallacy or technical debt.
Yeah, exactly. But it's an emotional sunk cost fallacy as much as anything else. So
no, I mean, technical debt. When I hear technical debt, I think less about the infrastructure and that kind of, like frequently technical debt it's a term of like, you know, we've made a big commitment to this way of doing things and now switching makes it hard, or we have a debt that we've paid into this particular approach. But, you know, my experience with technical debt is it's in the heads of the engineering team for the most part, right? I mean, we built all these servers, we bought all this software and that kind of stuff. But the real reason you don't switch gears is because the engineers, like, they don't want to learn a new thing. They don't want to start over. And, you know, it's scary because by definition, when you switch, you don't know the new thing is going to work. I mean, I think about Tesla's decision to take the radar out of the cars, which I think it's an amazing study in willingness to back off of that kind of stuff. Like, I cannot think of a single other self-driving car effort that ever reduced the number of sensors on the vehicle. Like, you know,
usually it's sensor creep. Usually it's growing they go up like a bug with all sorts of things on it. So
I made the joke about so I have a place in San Francisco and I'm frequently up there, and there, you know, the cruise cars we have the habit of going for a long walk in the morning. So we'll see 20 cruise cars, you know, driving up and down the Embarcadero or whatnot. And recently, sometimes we'd be walking up and down the Embarcadero. You could see 4 of those Jaguar Waymos, you know, like just coming down the street. Like there were so many of them, and they're like Christmas trees. You know, they've got all this stuff hanging on and spinning, and
it's definitely easy to recognize them.
Yeah.
I'm really curious about, so to get back to it, number one, I want to ask you about refactoring of neural networks, because I've done refactoring of code before, but as kind of more of a researcher, you know, it's always like, I'll just build the thing bigger, and if it works in a lab condition, it's fine. But I don't really understand from a fundamental level how you refactor a neural network as opposed to code. So I want to talk about that. But I also want to talk about hardware 3. Like, just real quick, do you think that hardware 3 is powerful enough, or do we need hardware 4? Do we need another order of magnitude faster?
So there was a thing when I got asked this question about hardware 2 before hardware 3 came out. And I spent a lot of time thinking about it. And in retrospect, so the more hardware you have, the bigger neural networks that you can run. The bigger neural networks you can run, the less refinement you need to get to a certain level of capability,
yeah.
right? So having faster hardware will get you there sooner. At the same time, I think it is true that once we really get a technique down, because it takes, the first time you get a technique working, I think you need like 100 times more hardware capacity as once it's really mature and it's really been refined. So, so the hardware requirement to do it kind of goes like this, right? But then we've got this other weird conflict. That's on a log scale, by the way.
Right. So it's big.
Yeah. But then you've got this other thing going on, which is the compute available to use for neural networks, because ASICs are still coming into their own. The neural networks so far, we've been running them on hardware that is actually really spectacularly poorly suited to running them. Like, we can do so much better. So the hardware you can get your hands on is been getting so much better so fast that the intersection of the interaction of those two things has been such that it kind of just ends up making more sense to throw more horsepower at the problem and raise your standards. And I think that's kind of where, Tesla is at, right? Like, there will be a hardware 4, and I think we'll see 5 and 6, right? And there will be more and more power. And the reason to do that is because, hardware 3, like those chips that Tesla puts in hardware 3 right now, those FSD chips, they're $20, $30, something like that, right? So they can probably, for the same money, those are in 14 nanometer Samsung process, right? Yeah. Okay, they can do a 5 nanometer TSMC right now if they want to. So which is the same price, right? It's not a more expensive chip compared to like what they were paying on the other stuff. So they can get 5x, 10x the compute in the same price envelope, in a lower power envelope. Like, why wouldn't you do that?
Right? Oh yeah, for sure. So
the longer it takes them to do it, the more the power they can afford to use is just going to keep going up and up. Right. And so, but I think the delays are mainly, the autopilot research team and the labeling team figuring out how to do the problem. Like, what's the right structure for the neural networks? What's the right question to ask? What's the right data to feed in? And then there's all of this training. Learning to train really big neural networks is super complicated. The hyperparameter space is super rich, and it's a research project, and it's taken a while for them to really get their hands around the problem. And I think they'll go to market with the hardware they have once they figure it out.
Because I was thinking about that. So I was like, for a while you were talking, I was thinking, wow, so if they just had, if they just took a car and just put a massive amount of compute power in this car, not that you could ever drive that around as a real car, but that would be able to do full self-driving. But you're saying it's actually more fundamental than that.
No, you can't do it with any amount of computer power right now.
Right, because they just don't have it quite right yet. It's still, yeah. And I think that's valid. I mean, I have I didn't say this before, but I have a startup company that's an AI-based thing, and we're doing a machine learning product as our first product, and it's a much smaller thing than full self-driving, but it is so complex. When you get to millions of hyperparameters, and of course they're at way more than that, it's so challenging to figure out why. It'll get to a point, this local maximum or local minimum thing that Elon talks about all the time is something that I have a great deal of empathy for. So what that is like when people, for the outside world, when you're training, at first, everything looks great. You get this nice monotonic descent and the error rate is going down. And then it just kind of goes, and it just sits there and does this for it, until you figure out some new way of doing it, you hit a bottom. And if it's not 0, then you're not at the global minimum. So you have to figure out what the hell it is to try to squeeze out more of that. And like you said, most of the time in research, it's just make a bigger network.
Most of the time with this stuff, it's find the bug in your code. Like
or your data. One of the big problems we ran into was we just had bad data. And we didn't realize it. We'd been pre-processing it in a way that had a systematic error in it. And we were like, it was one of those.
I tweeted out a link to this Yannick Kill.
Oh, he is amazing. Yeah, Kilter.
Okay.
Kilsner.
The thing he published yesterday, watch it. You will love it. It's not that long, but it's a guy. It's an interview with a guy who trains big models. And the thing that's cool to listen to, like you might not get, there's a lot of technical vocabulary and specialized stuff that's going on in it, but you can tell from his attitude and the way he talks about it, what it's really like to, because you read the academic papers. Right. And they make it sound like it's under control. Oh, we have this theoretical problem that we're looking at, blah, 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 blah. And the reality inside the lab is you're just like throwing all these different kinds of things at it. And, the breakthrough is, I left out a semicolon, right? That's the breakthrough.
Right? Good God. I mean,
he had a thing where he was talking about the Hugging Face guys, or is this right? The Hugging Face guys, they're working on 100 billion parameter language model, right? And they were pounding that they've just had this problem getting past this particular point. And then they finally drilled down in the data and they found they had these files that were like 500,000 backslashes in a row.
Oh gosh.
Complete nonsense. And it was just like completely, it was trashing their training would just hit those things and it couldn't digest that. And that was preventing the thing from moving further on. But also OpenAI, they have this, they have the, I really like using PPO for reinforcement learning. I think it's a really beautiful algorithm.
Can you explain that more? PPO for
reinforcement learning?
Yeah.
Proximal Policy Optimization. So it's something that would get pretty technical, if I get too deep into it. But here's the deal is, the math is pretty simple for proximal policy optimization. When I say simple, what I mean, it'd be pretty hard to derive it yourself. It was the people who came up with it were very clever, but they figured out how to fold all the different constraints that you want in a policy optimization thing into a single equation and just optimize on that. They figured out a clever way to do this. So it's just so beautiful as an algorithm. It's so clean and it's so simple. But the thing is, every single implementation of it has bugs because there are bits of it that are kind of hard to get your head around, right? So OpenAI, they have a reference implementation on the thing. Because it doesn't seem very hard, it's tempting to sit down and just implement it yourself. I have done it. And right. I'm not, super deep data scientist guy, right? But I built a PPO algorithm just to do it. But it's really hard to track down all the bugs. And the bugs are really simple and subtle. And the only way they manifest is that at the end of the day, your thing doesn't get as good as it could be. But the thing is, you don't know how good it can be. So you never know if you have a bug or not. And the way that you get bugs out is you go through the code and you run all these tests, and you just have to kind of exhaustively go through because there's so many little subtle ways it can be just slightly wrong. And you're not getting, that's very different from if you've written apps or whatnot, you get a bug, it crashes or the wrong output comes out and you can just backtrack it and you can find the thing. So debugging regular code, it's a pretty well understood process. There are ways to do it. You can write tests that will reveal it. But in neural networks, especially the way we are right now, because we're on the cutting edge, all of these things are new. We don't know how good they can be. So if the only clue you have is it's not as good as it could be, you've got no clues. You just have to read the code again and have somebody else read the code, talk about the stuff, do a separate implement. People do this. They'll implement the same thing 4 different ways.
Right.
And then try to get the same answer out of all of them as a way of doing it. It's just really, really hard to do. So OpenAI, I think it was Ilya Sutskever that had said, no, it was Greg Brock. And he said, basically, they were doing the StarCraft thing, not StarCraft, they were doing Dota, but, they had this really big PPO optimization thing they're running on this very sophisticated computer game that you play. Their goal was to play against, and they were way down the road of training this huge thing, and they found a bug in their PPO algorithm. Right? They've been using it for 2 years, and zillions of people have looked at the code, and they found another bug. And as soon as they fixed that bug, everything just got better. So it's no matter how much effort you put into finding bugs, you haven't put enough. And until you get all the bugs out, you're never going to get the results that you could be getting out of it. It's a really different code development process in very interesting ways than regular code is. And it's not super well appreciated, to use Elon's words. Right? This is not.
I think, it doesn't really hold, but there's some analogy to when I was a kid learning coding. There was no SDKs. You typed the code in a text editor basically and copied and pasted it in. And if it worked, it worked. If it didn't, you crashed. And so there's a lot of tools, including like code completion tools now and everything, right? So standard basic, or, traditional type coding is a kind of a mature technology at this point. And neural networks, I mean, relatively speaking, and neural networks are not. And also they're just like, you're going from code that you give a specific input and you get a specific output. So it's pretty easy to tell if it's right or wrong, to neural networks that are giving you kinda.
Yeah, they're distributions, right?
Yeah. I mean, yeah, that's what it is. It's probability distributions. And it's so difficult to know whether you've reached the global maximum, minimum, whichever way you want to call it, or whether you've hit a local, and why. Especially, I think,
especially when you're doing that. It's if you're re-implementing MNIST, right? You can look at the 1,000 other people who've done it, and about what it should look like. But if you're the first guy building a vision-based, highly modular self-driving car using all kinds of novel, model representation techniques and stuff like that, you don't know what the possibilities are.
Yeah, it's crazy.
Absolutely. I got a lot of respect for the people who do that, man. It seems just like dauntingly, frighteningly.
Right. And there's so many real world consequences to it too. If you're releasing this to the public, if you make a mistake, you could kill somebody. That's like, dang, you really don't want to make a mistake.
Well, it's that 2018 accident. So I've heard anecdotally that the development team in Tesla didn't take it so well the first time they had a fatality.
Geez. Wow.
And and that's a thing too. Like they have the advantage, like, inside Tesla, they can look at the statistics.
Oh, yeah.
You can make a couple of assumptions. You can say, this week, statistically, we saved 5 people's lives, right?
Right.
You could come up with that model. And after some point, that becomes consolation. If you make a mistake somewhere and somebody gets hurt, you have the consolation that statistically there were these other 100 people that you helped, right? And so there's some kind of balancing act to that. But early on, I mean, that was AP1, the early version. Yeah. And
was it the semi truck where it was kind of flat on? Yeah, because that was a radar sensor fusion thing, if I'm remembering correctly. That the radar and the visual were having, because radar is very, very non-localized. In fact, Elon just tweeted about that. He was just saying that if there was like super localized radar, that it might work better.
High resolution
in his, but I mean, because I think what, radar kind of goes out and it then gets a signal back, but it's not high resolution. It just says whether there's something in front of you or not.
The radars that get built right now are mostly like, and Mobileye wants to, they were working with Intel to develop higher resolution stuff to try to address that. But the failure that they had in that accident, and the failure that has bit them a bunch of times, is that the radars that get used in cars right now are Doppler radars, right? And they measure something relative to, you send a radar signal out into the world and it bounces off of everything to come back. Right. And so in the zero velocity bin, that's essentially the Doppler signal that comes back, you break the signal up into all these different bins, so you have a bin for everything that's moving at zero velocity, everything that's moving at 1 mile an hour, 2, 3, 4, 5. And this filter has very sharp edges. So if you ask it, just show me the stuff that's moving at 5 miles an hour relative to me, that's all you see. Like everything else drops out. But if you want to see a stopped object, it has the background noise of everything in the environment, right? So the signal to noise ratio in the zero velocity bin is terrible. It's just really horrible. Right. So this is why radar has a problem with objects. These Doppler radars have a big problem with objects that aren't moving. Like detecting a truck that's right in front of you can actually be quite hard, because the signal return that you're getting to it is being swamped by the signal return from like all the pavement and all the stop signs and all the buildings and all the trees. Like those might be weak signals, but there's a lot of them. And so they swamp that and you don't get a good return. So, in the accident where you've got a truck crossing in front of you, the radial velocity relative to your car is zero.
Right.
Like that truck is in the zero bin. So it can be really big and you can't reliably see it. So in that case, the car's driving along, it sees a white truck against a white sky. That's what the vision is. So the vision is already like, is that the truck? They don't see trucks from the side that much. It's not heavily represented in the database. So it's not super good at trucks in that situation. So the video is coming back and it's saying, I think there's a truck, but I only have 10% likelihood or whatever the deal is. And the radar says, oh, there's nothing there. Right. So then
it's like, it's a bridge, it's background, it's, all the crap around. Yeah. So just.
I think that is really central to why they finally got the radar out, which took some guts because the radar definitely adds value in a lot of situations. But radar and vision, they have a set of situations where they both fail. And so if you have two systems that you're relying on and they have independent failure modes, and one fails one time in a million and the other fails one time in a million, well, it's one time in a trillion that they both fail if they're really independent. But it turns out that radar and vision, they have some non-independent failure modes. And one of them is when you have a strange vehicle parked at the side of the road, like a fire engine is parked at the side of the road and its bumper is sticking into traffic, right? I mean, the vision system doesn't see a lot of them. It doesn't necessarily see them in, all different lighting situations and whatnot. It's an unusual vehicle, which is not to say it's rare. It's just to say that compared to when you look at all the other vehicles that are on the road, it's unusual. It's at a weird angle because, it's not in front of you. It's not sideways. It's pointed at this thing. The vision system has to precisely understand the boundaries of that vehicle. And, some of them, they've got, things that stick out and whatnot. And, so the vision system's trying to draw a bounding box around it and understand if it sticks out. And you're coming up on this thing and the radar is telling you there's nothing there. So that's really undermining the vision's confidence and its ability to make a decision. So in a very weirdly paradoxical way, you take the radar out, and even though you lose the radar's support in a bunch of situations, but you lose its confounding effect in a small number of situations. So there's this trade-off between how much is it helping me in the situations where it's helping me, and how much is it hurting me in the situations where it's hurting me. And in a super non-intuitive way, it turns out the places it's helping you, you really don't need the help. And the places it's hurting you, you really need the help, right? And so on balance, you get this very weird calculus that basically works out to, if you take it out, the system's going to work better.
Right. And I think also that goes to the, again, back to the data set. You've got biases. I always teach when I talk to my students about this, I'm like, if you had a data set, just to make it really obvious, with 99 pictures of a cat and 1 picture of a dog, your neural network, a real simple neural network, can just learn that all it has to do is just say cat, and 99% of the time. And so if you take these situations of a truck or an emergency vehicle on the side of the road, it's way less than 1% of the time. I can't even, it's at least a month or two since I've seen that last time. And what 99.9999999 something % of the time, I'm not going to see that. And so you've got an incredibly biased data set that is saying that's not an emergency vehicle, ignore it. And it's really important for people to understand how challenging just the data aspect of that is.
Curating the data set. You want a particular statistical, and I don't know how many of Karpathy's talks about like how they train the network that you watch, but they actually do a thing. They have this big network. So things have changed, but so at one point they had this thing. It's called Hydranet. It's coming out finally, but they called it Hydranet because it had a ton of heads. So on a neural network, when you have multiple outputs, frequently what you do is if you have one or a small number of inputs and you want to correlate them, you bring them all together. Then you have a stack of layers in the middle where you let it mix all that data and cross correlate everything. Then you bring it to a latent variable at the top, some internal representation, and then you derive all of your different outputs off that. So you might have a little neural network sitting on top of those for this output and a different little one, So when you draw the diagram, it looks like a snake that's got a bunch of heads, right?
Right.
And this is where the Hydra network thing comes from. So they actually do a thing where, they have a curated data set, but they know that they want a certain statistical distribution to train this head, say if we're just talking about the heads, and a slightly different distribution for that. So you can use a certain, cross-section, statistical cross-section of your training data for a particular part of the network. Because when you're doing your back propagation, if you don't want it to affect certain parts, you just fix those variables. You can back propagate through them, but not, you can calculate the gradients, but you don't update those variables.
Right.
So they actually do a thing where they've got these curations that they've sliced the data different ways, and they want a certain mix for this part of the network and a different mix for this part, and so on, right? And so one way to go at the, if you have a part of the network that you want to detect emergency vehicles, you can overrepresent emergency vehicles in there. Right. And you can get a better, and you can dedicate it. And so that's an example of where you can use engineering to try to overcome the gross characteristics of the system. But then at the other extreme, you've got the GPT, kind of thing. Like if you have a big enough network, right, and you train it,
learn everything,
right? It just learns everything, right? And they just, it's an engineering challenge to figure out like where's the sweet spot between how much effort we put in and what resources we require, and
right.
So, and that's constantly evolving. Now that they're doing auto labeling, like I think all the rules really changed pretty dramatically, because both the quality and volume of the data that they have available with the auto labeling system really changes the game in a significant way.
And I have to say, from like AI day, when I just coming from 3D animation background and stuff, the simulation engine that they have is super cool. And it's really fascinating how much they worked on trying to make it fool the sensors, essentially. So what they're trying to do is make it look so much like real world data that the optical, not necessarily the cameras, because that's, but basically you take the cameras out of the equation and you just input directly into the network from there.
They had camera models. Did you catch that?
Camera models, yeah. Yeah, and with all sorts of tweakable parameters, so you can make it look like it's at night. You can change the lens aberration, the chromatic aberration. Very cool. That's
the thing. But the whole, like, we went and we measured the characteristics of the cameras in our vehicles, and then we add a layer to the simulator engine to fold those characteristics in, so that, because you want, the problem with mixing simulated data and real data is that the neural network really quickly figures out which is which. Right? And if it's easy to figure out the difference between those two, it treats them differently. It just learns to do that really quickly. So the whole photorealism, trying to get arbitrarily photorealistic stuff and mix it straight into your training data, it's always been a bridge too far. Well, as far as I know, nobody's ever really solved that problem, but they're obviously trying really hard. Like if they're doing optical camera models and they're folding that into their simulator, that's something else.
Yeah. And that was, of all the things that I was like, wow, I would love to go, take a sabbatical and work with them for 6 months or a year, until being as old as I am, I don't know if I could last more than 6 months or a year, because it sounds like it's pretty intense there. But I would love to go and work on that, because I think that is just a fascinating, because it gives you the ability to anything, whatever it is that you need data for, even if you've only got 3 instances of it ever, you can make an infinite number, as long as the neural network can't figure out that it's all fake data. So.
I would be surprised if they're actually using the simulator to generate data that goes into the base training corpus. But using the simulator, they had an example of where they drove through a situation, and they didn't get the behavior that they wanted to. And it wasn't clear exactly what was going on. What you really want to do is drive the situation a bunch of different ways, vary things, and try to understand what is affecting this. So, the auto labeler is already taking clips and building 3D models out of them. So they take that 3D model out of the auto labeler, they drop it into their system. Now they can drive the neural, because even though if you take a neural network that's trained on real world data and you just run it in the simulator, that's a different space of problems than if you're trying to use a simulator to make data for your training set, right?
Yes.
You can take you take the real world thing, you run it in the simulator, and now you can do all the, what if it was winter and there were no leaves on the trees? Or what if the sun was there and it was a different time of day? Or what if the pavement markings were better or worse, right? What if what if a car was coming around the corner right at this spot? They can play all of those games. And so it gives them a super powerful debugging tool for dealing with really subtle sort of interactions between the planner and the perception stack. And I thought that was really cool that that the system was good enough that they could do that, and that they had tools that would basically automatically construct the scenarios for them so that they can do that debugging.
Yeah, it's really mind-blowing.
Like, their tools are so much better than I would have. I mean, they haven't been doing it that long. They don't have that many people. The teams are tiny, right? And they have all this other stuff that they've got to do. The amount of stuff that they've got built is super impressive.
Right. Yeah, it's humbling. Just like, just like your Japanese experience.
Like the SpaceX thing,
Yeah.
Like, it wasn't that big a company, but when they started landing rockets on drone ships, right? It's just, I mean, there's some really interesting thing going on with how productive they are in terms of, turning innovation into stuff that's actually paying off inside their products.
Yeah, it's pretty well. Actually, let me touch on this. Like, I'm going to save it for a whole other conversation.
They have their own hypersonic fluid dynamics simulator that they built from scratch for simulating the combustion in a rocket.
It's just like no big deal, right?
Yeah, that is so unbelievably hard. That's an open research topic, and you just built one.
Yeah.
Or the whole. I mean, we're gonna operate the pump that feeds oxygen into the tail end of the pre-burner, right, at 800 bar of pure oxygen, and we're gonna run that across metal. So we're gonna have 800 bar of hot oxygen running through a steel vessel, and like, really? Where are you going to get that steel? Right? And they're just like, hey, we'll make some new metal.
Right. Really? I know.
How long people have been working on that problem?
I think people don't understand that this full flow stage engine is insanity, because you can't test it piece at a time. Basically, the whole thing has to be operating at once in order to work. And the fuel side is whatever, but the oxygen side, pure oxygen, it just wants to eat everything.
Hot.
Hot pure oxygen.
Hot.
Yeah, it wants to eat everything.
Yeah. Like,
so it's absolutely crazy.
It makes hydrofluoric acid look like nothing. I mean, it's so corrosive. And they don't throw this engine away. They bring it back and they use it again. Like, oh my God. It's crazy. I love that anecdote where, it's American rocket designers had tried to use the oxygen-rich pre-burners, right, and had concluded it wasn't possible. Like, physics of materials simply didn't allow it. And then they found out after the Cold War that the Russians had been doing it when they got together, right? So you got all these Russian scientists and and American scientists or whatever, English-speaking scientists sitting in a room, and they have translators. And the guys on the English side are like, that must have been a mistranslation. Right. So they kept asking the question over and over again. No, you can't be doing that because it's impossible, right?
Yeah, I think it turned out the Soviets they just invented new metal themselves. Yeah. And I think the Soviet version of rocket development was much more like SpaceX. It's like, put it in there, fire it up, it's going to explode, figure out what the hell went wrong, fix it, and the American / German, the American German version was, don't even test it until you know it's going to work. And that's a very, very different paradigm. So, yeah,
super impressive. All of those.
So tell me about, what do you think about labor? Elon Musk is all about the population collapse and everything, and we can put that aside for now. But I feel like when we talk about companies like SpaceX and Tesla and Google and Apple and Facebook and Amazon, big companies, where where are they getting their talent? I feel like the people who can do this kind of stuff are really rare. And maybe I'm wrong. Maybe there's tens of thousands of these folks out there, but it feels like one of the problems that we're running up against is just human creativity. We don't have enough people who are smart enough in those areas. Or is that just a misconception on my part?
It's been really interesting to me. So, I mean, you and I, we grew up in an era, we grew up before the internet, and a lot of my ideas about labor and all that kind of stuff were formed then. We also grew up in an era where, like, you go to college and you learn your thing, and then you don't really learn after that. I mean, you learn how to do your job when you go to the, I mean, that's not true, but that's the way people thought about it. Yeah. I mean, the reality is you do a lot of, in fact, you know, my experience hiring people out of college is the first thing you got to have them forget everything that they learned, you know, actually learn how to
start over again.
But we, you know, that's how we think about this stuff. So it's been really interesting to me, like on a personal level, to watch how the world has responded in terms of sort of allocating labor to this explosion in machine learning. I mean,
right.
There hasn't been time for people to go out and write, you know, neural network textbooks that are up to date, and for kids to go through 4 years of college and come out and go into the workforce, right? Right. There's just not time to do that anymore because of how, and if you learned today all the stuff that there was, like if you had an up-to-date textbook and you went to college and that kind of stuff, you'd come out into a completely different world, like the techniques and all these. Like, the reality is that people learn on the fly now. And, you know, channels like your channel and other YouTube channels introduce people to this. Like, it's so easy to get an education in terms of the material being out there. And look at how many people compete in Kaggle competitions. I mean, they're huge.
Yeah.
The number of people who've taught themselves machine learning to the point that they're really useful.
Right.
You know, and they're right up to date is really amazing to me. I would, you know, if you'd asked me, I wouldn't have expected that this could be a thing, that so many people could learn to do it usefully so quickly. Okay. So I'm shocked, but I'm also shocked at my own ignorance that, you know, the reality of the world is different than I thought it was. And it turns out that, you know, if you build the tools the right way and you do the education the right way and you motivate people, if people are inspired to do this, that a lot of people will respond to that by getting to be good enough that they can contribute. Okay. Right. And so
I like that. I mean, I'll take, for example, Transformers. Like, you know, I didn't graduate that long ago with my master's. Transformers didn't exist.
Yeah.
When I think the first paper came out right around the time I graduated, but, you know, but it's like, holy crap. So if I just took what I learned there, it's totally out of date now because I don't know about Transformers.
Yeah, well, and Transformers will go away too. Just give it.
Yeah, and Transformers. Actually, did you see? I think it was Jan Kilchner who also talked about that. There's a Facebook journal article just came out saying there's a new version of a ConvNet that they say can outperform Transformers. So, you know. So
yeah, and I mean that's an interesting one because, you know, that one's been sliced 20 different ways also. Right. And so the whole question of, I mean, it almost kind of feels like if you got enough neurons, it kind of doesn't matter how you arrange them, right? Because for most of these really big models, you know, you get some state-of-the-art result with some particular architecture and training regime and whatnot. People really work hard at it. They do all the hyperparameter tuning and they do whatever. And then somebody takes some other significantly different approach with a different architecture and whatnot.
Right.
And then they do all this stuff. And it's interesting how often they converge to roughly the same performance. Right. And so there's some really good papers over from last year. I think it was 2020, basically asking questions about what are the characters, like what is the kind of information theoretic floor on how good you can get. Because given a certain problem and a certain distribution of training data, you posit this thing, if you could do everything perfectly, there's probably a floor because there's always some amount of uncertainty.
Right.
And how are these various techniques doing in terms of approaching that particular floor? And it seems like for a lot of the problems that people look at, especially these benchmark problems, that they are able to come up with enough resources, both in terms of their time and compute and that kind of stuff, that they can get pretty close to the floor. And so, like, even if you have a slightly inferior technique, you throw more neurons and some more data at it, and you get to the same floor at some point, right? So, I think transformer, the fact that you can do with transformers and actually convnets versus LSTMs, the convnets versus transformers is the second version of convnets versus LSTMs.
Right.
There were, people went and they looked at all these classic problems that you needed a RNN for, that you could only really solve with a LSTM or GRU or one of these recurrent neural network techniques, and they showed you could do it with convnets, right? And you could get after you tuned them up and solved the all the weird little problems having to do with the totally different structure of the neural network, you kind of ended up at the same accuracy if you had roughly the same number of neurons. And that went back and forth a couple of times. The LSTM guys would come back and they say, no, that's not right. If you do it this way, it's actually much more powerful in your convnet. And then the convnet guys would go, no, we can beat that. We do this. And you watch it go back and forth a couple of times and you're like, yeah, they both work is the answer. You can make them both work. And now we've got convnets versus transformers for image problems or speech problems, right? Audio problems, because you can do the one-dimensional convolutions for audio also.
Right.
And they get about the same result. It's cool that you can do. It would be interesting if it turned out that there was an optimal interconnect, that there was an optimal architecture. But it's almost more interesting to me that there's not. That if you have enough neurons, you make it wide enough, you make it deep enough, you get the training and the set about right, that you get close to the theoretical limit.
So I think it was Andre Karpathy had said after GPT-3 came out, he said, or it was either him or somebody else was talking about how he thought that a model like that could essentially model anything. Because GPT-3 is a language modeling thing, but essentially it's gotten, I don't even remember how many hyperparameter.
It's 178
billion?
170 billion parameter model.
Yeah. I mean, so it's absolutely insane. So, it was either he or somebody else was saying that he thought that essentially something like that could model basically anything. That it was flexible enough. I start to think about it like a human brain or something that, it's not like there's a different model that pops out for engineer versus artist versus, somebody who goes in the factory and screws bolts in all day. We're all born with more or less the same thing. It's just how the connections get made as we're kids. So circling back to early stuff that we talked about. But I mean, it does start to feel like maybe we could find some sort of flexible architecture that could learn pretty much anything. I want to talk to you about full self-driving and AGI because Elon Musk, and I'm starting to become convinced of this too, feels like really solving full self-driving is going a long ways towards artificial general intelligence. And I don't know if you agree with that. And maybe the Tesla bot is the thing that'll have to get there, but.
So there are these things that are technically true, and then there are these ways that we talk about stuff. And a lot of stuff that Elon tweets, right, are, especially when he's talking about AGI, I feel like he's responding to memes or concepts in the world using the language that people use to talk about that and not trying to be strictly technically correct. I think, it's true that solving FSD is a decent chunk of AI in the real world and a decent chunk of AGI, if you wanted to develop AGI. That's not to say that if FSD gets good enough, it's like AGI. There are things that you need to solve to get to solve these really big grand challenge problems. There may be 2 or 3 that you have to just really nail them in order to get the other stuff. And I think FSD occupies one of those boxes, or it requires one of those boxes to be elevated to a level of functionality that once you got it, you could turn around and you could stick it in your AGI, block diagram, and it would be a significant contributor to making that block diagram work too. But I do not think he's saying, because I don't think he believes, and I don't think anybody really believes, that if you just keep making FSD better, that you get that that you get, or that AGI is necessary for FSD, right?
No. In fact, probably we really don't want AGI in our FSD. We don't really want the computer making its own decisions about that.
When the robot uprising comes, we don't want them to have all the cars.
Yeah, and oh gosh, I don't even know if I want to open this rabbit hole because I don't want us to talk for 3 more hours. But the whole idea of self-awareness / consciousness fascinates me. Because we don't even know what the hell it is for us yet. And we're working real hard to create something that could potentially have that in the next 20 or 30 years.
Maybe it's, people debate whether, AGI is not well defined. Consciousness is not well defined. Like even people who study consciousness, they don't really agree on what the definition of it is. We don't agree on, whether there's a part of the brain that does it, whether it's an emergency property of having a sufficiently, there are big camps on both sides of that thing. Everybody's got their opinions. I have my opinions about what this stuff is, but my opinion is you don't need AGI to drive a car. And if you built an AGI, it's not necessarily conscious. That consciousness is something that you get by, it's a characteristic of the problem that you're asking the system that creates the AGI to solve. There are systems where consciousness is useful, right? Like what neural networks do is they become when you train them, they develop whatever faculties are necessary to meet the goal that you've set for them when you train them, right? And there are goals for which consciousness is useful. And I think if you built one of those goals in and you trained a big enough system, you get consciousness at the tail end of that. On the other hand, there are very few problems that we want machines to do that require that. There are some, right? Like if you want a machine to be your companion, if you want a machine to be able, there are certain places where the machine being self-aware, conscious, whatever, could definitely contribute to that thing. But it's a pretty small slice. And most of the practical things that we talk about, we don't need to structure the problem in such a way that the machine needs to develop consciousness to do it. So to drive a car, I don't think you need to do that. To solve math, to write music, for that matter, there's the whole Chinese room thing, right? Like I think that's you can mimic consciousness arbitrarily well without actually being conscious. And that's good enough for almost everything that you would normally want.
Now you're touching on my opinion about consciousness, which is that it's an emergent property of complexity, and that functionally, I believe we actually will get something that's conscious, but that it's just that we are not. We don't even know what the hell it is. But I don't think consciousness is as much as we think it is. I guess that's it. It's the primary thing to me is the modeling of others. I don't know if you ever read the book Born to Run. It's a fascinating book, but it goes back to the sort of evolution of humans, and the person, I can't remember the author. Sorry, I'll put it link in the description, something. But anyway, he posits the idea that the human being, like our very consciousness, came about because we had to pack hunt through. We couldn't run very fast, but what we could do is run for a long time, and so we could basically wear down our prey. But we had to be able to model that prey. We had to be able to understand what it was likely to do next. And that's the reason why I feel like full self-driving is kind of edging into that, because it's got to drive and it's got to model what that person, I don't know, when you drive, do you think sometimes you're like, oh, that's one of those kind of drivers. He's likely to pull out in front of me and cut me off before it happens. You kind of like, I don't know how we judge that, but there's little micro signals from the way somebody else drives, and that ultimately to be the best driver.
Lex Fridman's in your camp, right?
Yeah. Well,
I really disagree with him.
Okay, no, it's fine. I would love to disagree about that. But yeah, I saw an interview he did with his dad where his dad was saying that consciousness had to be embodied. And I feel very strongly that a computer that's just inside a box will never become conscious in the way we think of it.
There are a lot of people in that camp of believing that embodiment is super important, or to soften it a little bit, that if you're embodied, you get there a lot quicker than if you're not embodied. It's a lot harder. That's the softer version of all of these arguments.
Right.
No, I'm with Jim Keller. Like, I think, driving is a ballistics problem. That is not to say that
Really
that's the way he
complicated.
puts it, and it's
Yeah.
and I think that's approximately right. I do think that when humans drive, they engage all of these social faculties that we have, but the reason we do that is because we do it reflexively. We don't necessarily do it because it's making our driving better. And I think if you sat down and you got your clipboard and you sat there and you started asking the driver, predict what that car's going to do, predict what that car's going to do. Use your social faculties to predict. What you're going to find is they're wrong as often as they're right. Like, it's not.
Yeah.
Now, that doesn't mean they might believe it's helping them, and I think for a lot of people they do believe. My guess, my strong belief, it's a guess and a strong belief nonetheless, is that the externally visible, body language of a pedestrian standing on a street corner is something that, you can convert that into a pose model. You can map poses against a probability distribution of whether they're going to step out in front of you. And it will be quite good. And it doesn't require you to read the pedestrian's mind.
Okay.
For example, and I think that's probably true of cars. And so, I think that the machines are likely, I think emotions, like the social sort of components of, we're animals that are evolved to live in a tribe, and your pecking order in the tribe is a super important component of survival.
Right.
People are really focused on that. So things like their social status and their how other people think of them and all that kind of stuff. These are super important things that we think about a lot. And that's a faculty. I'm autistic, so I'm actually I have a lot of deficit in that space. But my observation is that most people have this amazing ability to read other people's minds and predict what they're doing. And it's a thing they can't turn off. They use it all the time in all of these situations, and their emotions are strongly, like, they're, your animal sort of instincts and responses your emotions are powerfully tied to these things. And so when you bring that to play in a situation where cars are driving down the road, you get like road rage. You get people acting like jerks and whatnot because because they're engaging those social faculties that they can't turn off. And is it making them better drivers?
Right.
No, it's not.
No, I know for a fact when I get upset with somebody else or competitive, sometimes you're like, jockeying for position.
It's the dumbest thing ever.
Yeah,
right?
It's stupid.
Yeah. And even if you win, you don't get anything out of it. It gains you nothing.
Like,
yeah, no, it's the dumbest competition in the world. And yet we engage in those kinds of things. So, yeah, like, do I want a car that wants to race the guy in the next lane over? It's modeling him and responding to him that way. Right? That doesn't seem good. I mean, I know you wouldn't necessarily go there, but that my opinion on the thing is that social dynamics, and understanding or trying to understand what other drivers do is actually a net negative. And that it's hard to make it a positive. And I know there are people who really disagree with that because their experience of their own driving is that they really think about other people and they think it's really helping them sort of maneuver in traffic and whatnot.
Yeah, I spend all my time driving, modeling other people. But as a ballistics trajectory, I also am autistic, and I have it actually didn't realize, you and I are the same age basically. And so, nobody was autistic when they were a kid.
Yeah.
So
we became autistic when we were 35.
Yeah, because when it was acceptable or when people realized, but I just didn't understand that emotions to me are something that I learned. I was like, for me internally, of course, I have them and I'm understanding of them. But for other people, it took me forever to figure out, oh, that means that person's upset. It's a good survival skill, and it's really not that great.
And there's two autistics, we'll be 2 hours into a conversation. Neither one of us knows when the other guy's getting bored, right? so it's never going to end.
We have to do the, So for everybody who's watching, I know this is kind of like loose, but just consider this the start, and we will
Opening
be having a conversation about all this. And thank you. I really do appreciate it. And I also really appreciate that we are able to talk on a little bit higher level. I feel like you're still explaining a lot of things to me, but I'm like, okay, I can, hopefully hang with that. But I really do enjoy. I think a lot of people kind of do hand wavy stuff. And so I think it's fun to actually be able to drill down a little bit and talk about specifics and really go like, what does it mean to try to reduce the error rate, to optimize a function or something like that.
Yeah, how low is low enough? Because the perennial question that I get asked is, so when is FSD going to be ready?
Right.
Right. And it's like, how good is good enough? Right. It's super. That's so hard to answer. Right?
I'm having a heated conversation with my business partner, because he's very adamant about using mean squared error for our particular problem as our metric. And I feel like it's not capturing enough. I feel like what's happening is it's bottoming out. We're getting too close to zero with it. And we need something like you were talking about modeling things.
Yeah.
We need to open it up so that we can see that small error that still
is. It a classification problem?
A classic what?
Is it a classification problem that you're doing?
No, it's actually more like a GAN, but it's not really a GAN. So it's actually,
you looked at cross entropy and.
Yeah, see, I think cross entropy would be really useful.
Yeah.
It's a very weird, the data set is very non-Gaussian and very, very sparse. The very sparse part, everything is always sparse, but this is also really non-Gaussian. You have all the values are at these weird extremes. So it's having a problem modeling that really precisely. So anyway.
Interesting.
Yeah, that's what, when you said the PPO thing, I was like,
cluster it first and then deal with that.
Oh yeah.
I don't know. I don't understand your problem, but
no, well, I can explain.
Yeah, those are binomial, trinomial, those kinds of weird clustered distributions and stuff. That seems
right. Essentially, it's weight painting. So it's a 3D animation problem, and the data set is full of a lot of points that are zero, which represents no interaction between the skeleton and the skin, and there are the points that have values. A lot of them are ones or very close to one. So you'll have zeros, like lots and lots of zeros, and then values that are sort of like 0.8, 0.9. 0.95, and then a bunch of values that are like 0.05 or 0.1 or something.
Have you considered like doing a redistribution of those things so that, because I mean, if you can do a redistribution so that you like sort of exponentially expand the two ends of the thing, so that you're getting more resolution in the space at the two ends, then you can try mapping your inputs onto something which is closer to linear and less of a bounded binomial distribution, right? Yeah. It's like, I'm sure there are a ton of different ways to look at it. Every machine learning problem has this issue of like getting your head around the way to represent the model so that it maps on it. Because neural networks are a pretty constrained way of solving. I mean, they're beautiful and flexible and they have all this kind of stuff, but then they have all of these quirks that you have to.
Yeah. And data pre-processing, I don't think people realize that from the outside, but you don't just take a picture and feed it into something like AlexNet. You do pre-processing first to take the mean pixel value.
Unless you're doing raw photon counts.
Yeah, well, okay. And I got to give them credit for that. That's got to be, but who knows? Even with that, they may be subtracting the mean of the values of the images. I don't know. That's kind of
if you've got enough layers and you can train them, right? You can propagate the gradient through enough layers to then you can map anything onto anything, right? The whole clock problem, like you interpolating, if you have a video of a clock and you try to interpolate the movements of the hands, it's really hard for a neural network to discuss it. You recast it into polar coordinates and now it's obvious.
Yeah.
You have one neuron, it's
yeah, that's actually true. That's true. And I think that's one of the big things that I've been seeing recently with Karpathy and others have been talking about. how they're recasting things from bag of points to vector space objects. And that to my mind is the thing that's going to allow them to solve full self-driving. Is that once you start recognizing objects in the scene and you can track those objects as objects, not bags of points, that makes all the difference in the world.
It's easy to see. It's easy to imagine that is going to be a big step forward. Is it the last one? I thought all the way through AP1 and early stages of AP2, like I was driving the cars around like a madman and trying myself to analyze the failure modes and try to understand what was going on. And I felt like, man, if they just could model 3D surfaces,
Right.
And, that was going to be, and then I spent so much time thinking about how to do it. And the BevNets turns out to be a really great way to sort of stimulate the system to understand surfaces in space and that kind of thing. And man, I got to say, from the driving characteristics of the car, they've got that 3D surface thing down. The road can be doing this and, with the lines going all over from your perspective, and it just gets it now. It's very good at predicting like the curvature and slope and all that kind of stuff of the road ahead of it, even when it's windy and curvy and, and there's bumps and all that kind of stuff. And it used to just be terrible at that. And yet it's not enough. Right.
No.
You nail that and it reveals these other problems.
Right.
Now, not reveals, you've just you've leveled up, you haven't perfected.
Yeah. It's like each problem is a subtle problem that was being masked by, if you have a big problem where you can't map the surface of the road, the subtler problem of mapping the exact lane definitions of things might be masked by that,
it's hard to tell that the relative positions of two cars, 2 lanes over, right. You're not accurately modeling how those two are moving relative to one another. When your big problem is the freeway's curving,
right.
You're not mapping that.
Right. Yeah. I don't know if you feel this way, but it's I feel like highway driving for Tesla is too easy, so I don't even count it as full self-driving anymore in my mind. They've solved it so well that I really feel good on the highway.
They can't do it with the FSD stack right now. I don't know if
I know, right? Yeah, it's the old stack that they're using for it.
Yeah, and there's a reason for that, so FSD. So FSD is very heavily dependent on BevNets, right?
Right.
So it has an output representation, which is a top-down look that breaks the area around the vehicle into a 2D grid, where grid cells are filled or not, and they're labeled. Okay, so your output is this 2D grid that has some resolution. So computation at the output layer is very sensitive to how big that grid is, right? Because when the grid resolution goes up or the size goes up, the number of grid points you have to calculate goes up as a square of those dimensions, right?
Right.
So I was driving FSD. I found that you can if you drive FSD on a rural highway,
right,
that isn't marked as a highway, and you can find some. I found some on a road trip that I was on that. It'll stay in FSD up to 65. And when you go over its FSD, it falls out. So I could get on the same road. I could use it in AP or I could use it on FSD. So anyway, cool. I'm driving on this highway at 64 miles an hour or something. And I'm observing at what point the vehicle responds to things as they approach. Right. So now on AP has gotten really good at being able to respond to, say, trucks that are 500 or 1,000 feet away. And it used to only respond to when it was radar dominant. It tended to not make strong responses to things until they were inside the radar envelope, which is about 250 feet or something like that, right? And the car wasn't good at seeing you're coming up really fast on a truck that's moving 40 miles an hour slower than you are on the same line. Move over, it'd have to catch up to the truck and slow down and then move over. And so if you drive on highways, you'd speed up, slow down, speed up if there were a lot of slow trucks. And now it's a lot better at seeing the truck really far away. On the AP stack, on the FSD stack, it doesn't see it at all. The truck isn't even present until it enters the BEV map. Because the BEV map only out
which is limited. Feet. And of course, you don't notice that much if you're driving on a city because you might be going 40 miles an hour. So the grid size just doesn't matter.
The fact that so I think the grid size extends out a few hundred feet forward on FSD right now, right? And so I think that's one of the reasons that I have an 80-mile-an-hour speed limit on the thing, because how fast you have to respond goes up as like the square or the cube of the velocity, depending on what you're talking about. So the thing is, so 90 is a lot, it requires a much bigger grid than 80 does. Anyway, so
did you see like Lex Friedman did a class in 2017 at MIT that he recorded, and one of their problems was a little driving thing, which was a 2D thing to make your car go through traffic in a 2D grid. And I was like, good God, that's what they're doing with full self-driving for real now. It's a little Frogger game where you're trying to go through.
Well, I mean, of course, you can do tricks where you have some 2D stuff, some POV, camera POV stuff, and you try to mix it with the BEV, like you overlay those. But it seems like trying to get to the single stack is really trying to map everything into that BEV kind of window, and then making the map, the BEV view, big enough that it's got the time horizon that you need to function well on a freeway. It's not difficult for me to believe that is challenging to get that map big enough. Or I could be imagining things. But I was noticing that when I was on FSD, that the horizon for responding to things was much shorter than when I was on the autopilot stack driving on the highway. And I think, you definitely need to expand. They either need to fold in the 2D stuff, which I think is not a good answer. I think figuring out how to make the BEV extend far enough out is a better way to go. But then, do you go to a coarser grid? I mean, do you just eat the compute penalty of making the box that big? Or do you go to a coarser grid? And if you do go to a coarser grid, then now all your training and, it's like you have to do a fine grid and then a coarse grid laid inside the fine grid. Now you're counting redundant stuff in the middle. And it's not clear exactly what the right answer is.
Right. With my 3D animation stuff, of course, like a lot of gaming and stuff is LOD, level of detail. And so you just remove detail as you go further away. And I wonder, the problem is you need more detail the further away you get because the pixel count is smaller, right? So a truck is tiny when it's really far away. So you actually need a finer grid up there, essentially. But maybe they can do a trick where they can do a coarser grid, doing some sort of a algorithmic LOD or something like that. But that is interesting. And also I have a couple of highways right near my house. I didn't realize that it was a switchover at about 65. I'm going to go up because they have traffic lights, and so they don't count as real highways. And so it still does the regular FSD stack, not the autopilot. So I'm going to go out and give that a try and just examine that, like exactly the same road, and see what it does when it's a little faster. So
cool. I was on a rural highway in Utah when I happened to notice this. And this was on 10.3 when it had the crazy. So I had noticed we're driving in the middle of nowhere, and I can set the speed whatever I want. There's no other traffic, but there were shadows on the road that were triggering phantom braking. Right? Oh yeah. So I was measuring the distance to when the shadow would enter the BEV stack and trigger the phantom braking.
That's pretty cool. I wonder, we get that really nice visualization, but I don't know that it covers as far as it actually goes. It'd be cool to have a little bit more, less pretty, but more scientifically accurate version of that, optionally. It would help to debug.
There are a ton of things that was Trevor Rice Fry has been posting these 3D extractions, which is really cool because we can see what the raw size of the grid being output only for the static maps right now. There's got to be a dynamic one in there, and it's the dynamic one that I'm thinking is probably limited in scope right now. Right. And that is leading to some of these speed-related issues.
But again, this is why I wonder if them being able to move from a bag of points to objects, vector objects, will alleviate that to some extent. I don't know. Maybe they're still on a grid even when they do that. Because if they can identify a truck as a truck as an object, it doesn't really matter how far away that truck is because it's identified as that, but it still may have to overlay that on a grid.
It's possible you can go to a much coarser grid.
Right.
And still identify objects. And like if you have the bag of points output, right, and you have a C program looking at the bag of points, and it's trying to like count how many pedestrians you have or figure out if that's a pickup truck or a van or whatever, you know, at distance, right? It needs a certain, I suspect that a heuristic needs more, it needs more resolution in order to be able to discriminate things, and that a neural network will, you know, taking an equivalent output would be able to work at lower resolution and still give you good answers, because it can look at the interaction between a lot of different subtle properties of the grid cells in order to figure something out. So it's possible that when they go to bag of points, they can cut the intermediate grid size, you know, they can stay with the same grid and make all the boxes twice as big and it still works. Like that could be a big win, right?
Right.
If it's true.
And they do have the advantage of having temporal now. So rather than individual images, it can look at something over a whole bunch of sub-second frames and go like, is that a truck? I think it's a truck. I think, you know, so the probability can increase for distant and difficult to detect objects, you know, over time. And so it can actually use that to build up its probabilities.
I like that, like I knew that they were doing the successive frames thing but they have two different kinds of memory. They have a distance-based memory and a time-based memory. Did you see that thing? Yeah. I thought that was so clever because I had wondered, you know, I had actually thought about that, you know, you come to a stoplight and your memory kind of decays away because you're just sitting there at the stoplight, right? Yep. And like having a separate distance-based memory where you take a frame every so many feet, because that memory persists. You're not moving, so it's static. Yeah. Right. It lets you remember, oh, there was this sign, you know, 50 feet back, which is still relevant because I'm still at the same intersection. Or, you know, or you could see a car that you passed and know that it, or suspect that it's still there. Right. I don't know. It was
or things that are occluded, or I mean, it's it's a very clever. Again, I don't know. Conceptually, it's like great idea, but how you implement that, I'm like, holy crap. So
I mean, they have the IMU, you know, they have odometer ticks, and so they have two memory stacks. This was the diagram I saw. They have a memory stack that's just a frame every so many seconds, right?
And it holds on to a certain number of those. Yeah.
And I think it's 16, right? Or at least, I mean, I don't know what it is now. At one point, Andre showed a diagram and it was 16, right? So maybe it's more or less now. And then the diagram that I saw, it didn't show 16. It just showed it has a little icon for a stack, right? But it had a time stack and it had the same icon for the distance stack. So I was thinking, well, now it's 16 frames of time and 16 frames of distance. And the distance stack, it's exactly the same structure going up from those two. It's just one is clocked according to the odometer ticks as you go. So one of them is like, you know, every 10 meters, and the other one is once a second or something like that. Right?
Yeah. It's just it's genius. It's really, really smart. All right. Okay.
So it's been 2 hours now.
I know. It's all right. We've hit 2 hours. Super interesting stuff to talk about. We will continue this on, but in the meantime, again, thank you so much. I'm going to let you go so you can have your afternoon there, and I can walk my dogs before it gets totally dark here. So, all right. Thank you again, James. I really appreciate it. I hope everybody out there, I'll try. The thing I'm going to do in the editing is try to put down what the hell we're talking about. When we say things like PPO and stuff like that, I'll try to like put down something about what that actually means. So hopefully people can follow.
Well, I'll send you the link for the AlphaGo video too.
Yeah, that'd be great. Thank you so much. I appreciate it. All right. Well, thank you again, and I'll talk to everybody later. Bye-bye.
Take care.